Good. Good. Now 2.6. 2.6. Okay. So remember plus 4 Latin is minus 4 Latin. Or inductive loss, capacitive loss. Okay. Now continue. Continue. 2.6. 2.6. You need to move. Yeah. From here. We discuss about how to calculate power and torque. Okay? Yeah, power and torque of synchronous generators. Okay? Yeah. You know, we have stator A over comma B over comma N C over comma. This is stator. So for the rotor, we have this one. Okay. Yeah. Of course, for the rotors, we need to supply DC voltage. You can guess DC current. But we have the questions. How can we rotate the rotor? Okay? How can we rotate the rotor? We need to use right mover. Right mover. What does this mean? Right mover. Right mover. We can use water turbine. If the water from the dam come down, the water turbine will rotate. And the water turbine has the same shaft of the rotor. Water turbine rotate, rotor rotates, and we can get the voltage. We can get the voltage. We can get the voltage. Okay? And A over comma B over comma C over comma, just, make the Y connection. Is it clear? So if we have thermal power plant, we need to use a gas turbine or steam turbine. No steam turbine. You know? So if the steam turbine rotates, that means the rotor rotates, and we can get the voltage. Okay, A, B, C. Okay, of course this one is line voltage, and between phase and neutral you get phase voltage. Is it clear? Yeah. So it depends on what kind of power plant we use. Steam turbines or gas turbines or water turbine. Okay? Yeah. We discuss about power flow, right? Yeah, power flow. Power flow. This is generator. This is a generator. So the input must be mechanical power, and the output is electrical power. That's right? Yeah. So we need to apply the mechanical power into the rotor. Okay, so if the rotor rotates, we need to apply the torque. We say apply torque. So here we have V is apply torque times what? Times omega m. Omega m. So omega m is mechanical angular frequency. Okay? Yeah, of course for physics, you also study power in torque times omega. Right? Yes. VI. VR. VR of generator is electrical power. So we have the formula. So I assume I use line parameters. Line parameters to cable. So now we have B three phase, right? A, B, C, three phase. Each one, A, three, V phase, I phase, go sidewise. Nope, come back. We have three phase angle, right? So when we consider phase and phase, this is theta. Okay? So this is cosine theta. Okay? So if I would like to use line parameters, we have B three phase A, so root of 3 line voltage line current cosine theta. Theta. It's up to you. You can give all phase parameter or all line parameter. It's up to you. But we know here must be theta because we have definition for. Okay? Yeah. Now, how many power losses we have? 4, right? Copper losses, mechanical losses, right? Stray losses and core losses. Okay? So now we have 1, 2, 3, 4. Okay. Remember that the power will flow from the rotor to the stator. Okay? So, for mechanical, we have delta B stray. That means stray losses. Right? And if the rotor rotates, that means we have the friction between rotor and bearing. We have the friction between rotor winding and the air. Okay, so we have delta B, friction and windage. Okay, and of course, here we have rotor magnetic field. We have rotor magnetic core, so we have delta B core. Delta B core losses. So here is rotor part. Here is stator part. Okay, so can you guess which one here? This is delta B CU, copper losses. Copper losses. Copper losses. Okay? Copper losses. So sometime here we have delta B CUF. What does this mean, delta B CUF? The copper losses from the rotor winding. Okay, because this one is IF, this one is RF, so you get delta B CU copper of a few windings is IF times RF. As well. Okay, so when we consider sometimes the core losses including delta B CUF, or sometimes delta B CUF will be here. Okay, it depends. Okay, it depends. So here is delta B CUF S. S means status. Or sometimes we say here delta B SCL, stator copper losses. And here is delta B RCL, rotor copper losses. Okay, so this is stator, this is the rotor. So you have, remember we have between rotor and stator we have air gap. Okay? Air gap. So the power from the rotor to the stator, we say B convert. Remember B convert? B convert. So B convert means we have the power conversion from the rotor to the stator, or vice versa, from stator to rotor. Okay, so sometimes we say convert this power, sometimes we say air gap power, the same. The same. converted power. And this is B convert. So B convert is what, remember the formulas? Tau induced times omega m. Okay, we discussed yesterday. Okay, induced torque. Tau in times omega m. Is it clear? Yes. Good. Yeah. Now, so if I don't want to calculate this convert power by these formulas, I can use another one. Because here is the operation of the air gap. So that means we don't care about stator winding. So we have B converse is also equal to 3 EA IA and cosine 1. Okay. What does this mean, EA? EA means internal, right? Internal phase angle. Internal does mean at the air gap we don't take into account stator winding. So we say EA. IA. So if we use EA and IA, how about the phase angle? Raman. So the power factor here is Raman. You get this one. Okay. So it's up to you. So if you know induced torque and omega m, you can get converted powers by this formula. Otherwise, if we know EA, IA, cosine Raman, you can get converted power by this one. Can we know EA? Can we know EA? Yes, definitely yes, because we have this equation. Right? For this equation, we know EA. We know EA, we know IA. Of course, if we know EA, we know IA, you can get the phase angle Raman, and we can get the converted power. Okay? You understand? Yeah. And I also explained to you, we can calculate the output powers based on line parameters or phase parameters. It's up to you. Okay, and similarly, we can calculate reactive power, three-phase reactive power. Okay, yeah. Three-phase reactive power. Okay, continue. This is Laplace law, right? This is Laplace law. And we have delta Raman theta. Okay? Yeah. Delta theta Raman like this. Okay? Okay? You know, and then this is the x-axis. This is the x-axis. This is the x-axis. This is the x-axis. And we assume RA is 0, I 0. Okay, of course, Laplace law. And RA is 0. Okay. Yeah, so here is V phase, right? It's V phase. And that means so this one is IA. Okay, the phase angle here is theta. Yeah. Yeah. And then because we don't have IA, so now the voltage equations become what? The voltage equation becomes V phase EIA minus IA SS. Right? We don't have IA. We don't have IA. So here, we can get J's XS IA. J's XS IAs. Okay? Right? Right. And this one is AI. AI. Like this. Like this. Oh, sorry. Like this. Okay? So this one is x-axis. This one is x-axis. And I would like to find the projection of EA into x-axis. Okay? Here. Here. Right? This is the projection of EA into x-axis. Right? And we know this phase angle is delta. This phase angle is regular. Okay? Yeah. So we can get the projection here or projection here. Okay. This is x-axis, so this one is y-axis. Y-axis. Okay. So the projection of EA into y-axis. Into y-axis. Is what? I mean this segment. This segment is AI times sine delta. That's right. Okay? Yes. So, continue. Now, we considering this one. This one. This is theta. So, this one is theta. Right? This is theta, so this one is by minus theta. This is by minus theta. Okay? Yeah. So now we have projection of this segment. That means the projection of J's XS IA into y-axis is what? Is XS IA cosine theta. Do you agree with me? Cosine theta is this segment divided by this segment. And this segment is the magnitude, right? The magnitude. So you get XSIA divided by this theta. Or this one is this one. Okay? Yeah. So 1 and 2. So 1 equal to, right? 1 equal to, because what do you consider this segment? So you get EA sine delta is XS IA cosine theta. Cosine theta. So we can get this formula, right? Now we have IA cosine theta is XA sine delta divided by XS. Oh, this is constant, so we don't need to take the actual, right? Sorry. So now we get here number 3, this formula. Yeah, this formula. So now we have IA is cosine theta. Now we have IA is cosine theta. So here we have IA is cosine theta also. Okay, so here is number 4. So if you combine number 3 and number 4, you can get this one. Okay, so now V out is 3 V face, right? V face. So if we have I face the same, you know. So I face cosecant you can this one. So now we have EA psi delta divided by XS. XS. Here. Here. Okay? We assume because we assume we don't have I. We don't have I, so we don't have copper losses at this state. So here equal to V convert if RA is 0. Convert. Right? 0. Yeah. You understand? Of course, if we know I, so if RA different from 0, we have B converse is what? A B out plus delta B CUS or delta B SCF. Okay, set the couple loss. You understand? So, of course, we can guess B max. B max if psi delta is 90 degrees. And you also how the condition delta should be higher than 0 and less than 90 degrees. So if psi 90 degrees is under this 1, so we can guess B max is 3 V phase EA, then divided by XS. Okay? Any questions? Yeah, any questions? Questions for you? What is this? What is this? This is constant. This is constant. This is constant. So this is the sinusoidal waveform, the sinusoidal function, right? This is a function of delta. Right? So if I would like to indicate the waveform of V out, now this is V out, this is delta, and you get this form. This is V max. This one is 90 degrees. This is 0 degree. Do you read me? Yes. Yes. So we only consider these regions. Maybe here is symmetric, you know. Because that is higher than 0 and then 90 degrees, so we only consider this one. So that is right. We don't have this one. Okay. So now I erase it. I just pick off. Yeah. That's okay? That's fine? Yes. Yes. Because after one circle, one cycle, repeats. This is B max. This is B out. B out come from what? B out come from generator. Come from synchronous generator. So this one is BG. G mean of B active. That means the power comes from synchronous generator. Okay, so if we have lot, now I have lot 1. Stay busy. Stay busy 1. Here, this is delta. So here we have lot. I said Y. We have Y. Y. A comma A, B of B, C, không C, is still a lot. So we have a lot power, I say V lot or I say PL is a lot. Okay? So the system is balanced if and only if we have parent point. This is PL or V lot, right? Right? So if we don't have lot, we don't need output power of the synchronous generator. Okay, now we know V lot. Now we know V generator. So this is balanced power point. Is that right? So if we increase V lot, now you get V lot overcomer. You get the new balance point. So this one is 1, this is 1 overcomer, something like that. Okay? Yes? We continue to increase V lot. Now you get V lot double overcomer. So V lot now equal to V max. Okay? And then very dangerous because if we increase a little bit of V lot, black out. You know, black out. Yes, the power system is running out. You know, that is the reason we need to limit delta A higher than 0 and less than 90 degrees. I mentioned before. This is the answers. Okay, so for safety, for reliability, normally we do delta A 30 degrees, so somewhere here. So this is V lot for reliability or for safety. Yeah. You know? Yeah. So if we move V lot, maybe here below 0. If we move V lot to below 0 to below, we have fluctuation, you know, we have fluctuation. And after some fluctuation, they get the balance. But if here, you know, if we have fluctuation and then just move down, the system is running out. Okay? So that's the reason here we limit the deltas. Yeah? Normally less than 30%, also 30 degree. So for the final exam question, I require you to calculate deltas. And you say deltas is 45 degree. Okay, congratulations. See me again. Right? See me again. Because it's relevant to the theories we discussed in this class. Okay? To be careful. There's some tips. So if you attend my class, you can have some skills to double check your answers of final exam is consistent or inconsistent. Okay? Yeah? So, time off. We finish the class today. See you Thursday morning. We continue slide 66. Okay? Enjoy your lunch.